What's up, everybody? So I've decided that I'm going to re-record this first week of lectures. And the real reason behind this is because, well, we've had some technical problems, right? This is no fault of y'all's, and I don't believe that y'all should be penalized for it. So for those of you at home who are watching these earlier week videos, and are like, no, not having it. Yeah, neither am I. For that reason, I've sat down with the tech folks as well as some other members of the department to kind of debug what these tech problems are the result of, and we think we've got them all pinned down. But for now, I'm going to quickly go over all of this week's material just so that you'll have something to work with, right? So you're not left out of the mix or anything like that. That way you have something quality to actually come back to and be like, all right, this is what the material is. Having said that, without further ado, section 1.1. So to start off with, section 1.1 is really just about graphs, right? The Cartesian graph. So to start off with, let's talk about the anatomy of a graph. A graph has two axes, a vertical real line and a horizontal real line. The horizontal real line is your x-axis, the vertical is your y. It's broken up into 4 different quadrants, and it has an origin point that sits at the intersection of these two axes. Well, this is all well and good, but how are we going to use it, right? How are we going to use it to plot points like this ordered pair here, -1, 2? Well, the first thing we need to know, or to recognize, is what this ordered pair is telling us. The first value in the point is telling us where along the x-axis it sits, and the second is where along the y value, or y-axis, it sits. So what this looks like is with this point -1, 2, we would plot it to be right here. Why? Because it's -1 along the x-axis, so we're going to move 1 unit left of the origin. That puts us at x is equal to -1. And then we're going to move 2 units north of the origin. That puts us at y is equal to 2. So in this way, our coordinates, our ordered pairs, they just tell us where we sit relative to each axis. That's all there is to it. Having said that, you'll notice in this example, we've got a collection of them. This is a set of points, right? And when we plot all of them, what we get is a nice lively scattered plot here. But we should note, scattered plots aren't the only types of graphs, right? There's line graphs, there's bar graphs, etc., etc. Having said that, there is something I'd like to bring to your attention with these graphs. You'll notice these little zigzaggy marks. All they mean is that you're going to skip a bunch of numbers. So you're going to skip a bunch of numbers from the origin up till 600. And then here you're going to skip a bunch of numbers from the origin up till 1997. So this little zigzag mark, it's just telling you you're going to skip things up until that first value. Alright, well, let's imagine now we have 2 points on a graph. x1, y1, x2, y2. We want to know what the distance is between them. Well, looking at this, we might notice that there's kind of a hidden triangle built into this graph, right? Imagine that we're to shine a light on this point, x2, y2, perpendicular to the y-axis. So we're at a right angle, we're shining this light. The shadow it casts would intersect the shadow this point casts, doing the same thing with a light perpendicular to the x-axis. It would cross, the 2 shadows would have a point of intersection, right? And they would intersect at a right angle. And in that way, we kind of have this hidden triangle, this hidden right angle triangle. Well, in the case of right angle triangles, we know how to solve for the length of the hypotenuse, right? solve for the length of the hypotenuse, that's just going to be a squared plus b squared is equal to c squared. It's a Pythagorean theorem. All right, well, this makes me think something, right? Because if we look back at what our triangle looks like, we say, all right, well, this leg is going to be, the length is going to be equal to the difference between y2 and y1. And this leg, its length, is going to be equal to the difference between x1 and x2. All right, so we know the values of these lengths. And using the Pythagorean theorem, we can figure out what that distance is. So to reiterate what I was just saying, this length here is going to be the absolute value of x2 minus x1. This length here is going to be the absolute value of y2 minus y1, the difference between those points, right? And using that, we can say, all right, well, that must mean then the distance between those 2 points, those diagonal points, right, that diagonal distance, it's going to be equal to d squared is equal to the difference in our x values squared and the difference in our y values squared. Well, knowing this, now we know we can take the square root and we can get the length of that leg, of the distance between those 2 points. Which brings us to the distance formula. The distance formula says d, distance, is equal to the difference in our x direction and the difference in our y directions, both values squared under the radical. All right, so let's imagine we have these 2 different points. We want to know what the distance is between them. Well, based on what we just said, graphing them, say, all right, this is that distance. This leg is going to be the difference between 1 and 4, that's just 3. This leg is going to have a length that's equal to the difference between -2 and 3, that's just 5. So using that, we know that this is going to be equal to the square root of 3 squared plus 5 squared. Or more precisely, I should say, the square root of the quantity 3 squared plus 5 squared. So doing the math, what we're going to find is the square root of 34, or approximately 5.83. And for those of y'all at home who don't recognize the symbol, this just means approximately. Having said that, I should note, I personally would prefer y'all to leave it under the radical. Leave it like this. Don't try to write an approximation. And I say that because mathematicians, we tend to be really picky. We don't like approximations when we don't have to use them. So if you can just write the square root of 34, just write the square root of 34, right? Having said that, let's keep moving. Actually, before we move on, I'd like to bring your attention to some of these suggested examples over here in relation to this distance problem, or these distance problems. I would like y'all to check out example 4, slide 19. It's a decent problem to get y'all going and to get y'all thinking about how you can use the distance formula and all the different variations of problems you could solve with it. So, this is all well and good. But what if we wanted to know what the point was that sat directly in between 2 points? Let's say we're given the point -5, -3, and the point 9, 3. How would we know, how would we find this center point? To find the center point, we would apply the midpoint formula, which all it's really doing effectively is averaging your 2 points. It says, all right, what are your 2 x values? Average those together. What are your 2 y values? Average those together. That's it. So the midpoint formula, it's going to say take x1, add it to x2, divide by 2. Take y1, add it to y2, divide by 2. Those are your new x middle point, y middle point. My mistake. I should say that is your new ordered pair, x middle point, y middle point. So, let's imagine we're given this problem here. Stop for a second, let y'all read it. What we want to do is we want to approximate what the sales were in 2004. We know 2003, we know 2005. So assuming that the sales moved in a linear way, we could approximate what the sales for 2004 were by calculating the midpoint. So to do that, we take the years, 2003, 2005, add them together, divide by 2, take that average, right? That would give us 2004. And then we would take the cells, add them together, the cells for 2003 and the cells for 2005, add them together, divide by 2. And then this gives us our new midpoint. This gives us the midpoint approximating what we think the sales were for 2004. Okay, so now let's imagine we're given a bunch of points. We want to move them, but we want to move them in a way that doesn't change the distance between any 2 points. One way we can do that is with a translation. We can translate a point by just adding or subtracting a value to it, right? So what I mean to say is, it'll be easier to show with an example. What I mean to say is, let's say we want to take this collection of points. We want to move it down to here in such a way that these 2 points share the same distances, these 2 points share the same distances, so forth, so on. Well, to do this, we would say, where do we want to move one of these points? All right, we want to move these points 3 units to the left, 3 units down. Are we going to do this? We're going to take the original set of points and subtract 3 from all of their x values and subtract 3 from all of their y values. And that's it. This is called, again, a translation. We're just translating our points down. Notice this changes the value of our midpoints, right, naturally, but it doesn't change the distances between our points. Also, having said that, sometimes we'll say if this is our original point, this new translated point will be represented with an apostrophe outside of our parentheses. So what would that look like? We would say this point, let me write it over here actually. This point, 1, 3, it gets moved to a new point, -1, 0. So just some notation. I'll sometimes use this notation, and I don't want y'all to get confused about what it might mean. It will also later come to mean something else. It'll come to mean the derivative, but those contexts will be hugely different from what we're currently doing right here. In that context, I should say. So, again, looking at these points, oh wow, I did bad math here. It's supposed to be -2, 0. Arithmetic mistake, they all happen, we all have them. But again, like I said, our original coordinates are new coordinates. All we did was subtract values from them, right? But we subtracted the same value from every one of our original points.